Azure Cloud VPN Options. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics, with a focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving into Azure Cloud VPN options, which are critical components for establishing secure connectivity between your on-premises infrastructure and Azure Cloud resources, as well as enabling secure connections between different Azure virtual networks. Understanding these VPN options is essential for architects and engineers designing hybrid cloud solutions or multi-region Azure deployments. Azure provides multiple VPN solutions, each tailored to specific use cases and connectivity requirements. These options range from site-to-site VPNs that connect entire networks, to point-to-site VPNs for individual client connections, to VNet-to-VNet VPNs for connecting Azure virtual networks across regions or subscriptions. Each option has distinct characteristics regarding throughput, scalability, redundancy, and pricing models. The diagram on the slide illustrates the three primary VPN connectivity patterns in Azure. At the top level, you will see Site-to-Site VPN, which represents connections from on-premises data centers to Azure virtual networks through VPN Gateway. In the middle, point-to-site VPN shows individual clients, such as remote workers, connecting to Azure resources. At the bottom, VNet-to-VNet VPN demonstrates how multiple Azure virtual networks can be interconnected. Each pattern serves different business requirements and technical scenarios, and understanding when to use each option is crucial for optimal architecture design. VPN Gateway Overview. The VPN Gateway is the foundational component that enables all VPN connectivity in Azure. It is a specific type of virtual network gateway that sends encrypted traffic between your Azure virtual network and other locations. Every VPN connection you establish in Azure relies on a VPN gateway resource deployed within your virtual network. When you deploy a VPN gateway, Azure creates two or more virtual machine instances that are deployed to a special subnet called the Gateway Subnet. These VM instances contain routing tables and run specific gateway services, but they are completely managed by Azure, meaning you cannot directly configure or access these underlying virtual machines. This managed service approach ensures high availability and reduces operational overhead. VPN gateways come in different SKUs, each offering varying levels of throughput, number of tunnels, and features. The basic SKU supports up to 100 megabits per second aggregate throughput and up to 10 site-to-site or VNet-to-VNet tunnels. The VPN GW1 through VPN GW5 SKUs provide increasing performance levels, with VPN GW5 supporting up to 10 gigabits per second throughput and 100 tunnels. There's also a VPN GW1AZ through VPN GW5AZ series that provides zone redundancy for enhanced availability. The diagram illustrates the architecture of a VPN gateway within an Azure virtual network. You can see the Gateway Subnet, which is a dedicated subnet specifically for the VPN gateway resources. The VPN gateway instances are deployed here and connect to different destinations, including on-premises networks through the Internet, remote clients for point-to-site connections, and other Azure VNets for VNet-to-VNet connectivity. Each connection type flows through the VPN gateway, which handles encryption, decryption, and routing. One critical aspect to understand is that you can only have one VPN gateway per virtual network, but that single gateway can support multiple connections simultaneously. For example, a single VPN gateway can maintain connections to multiple on-premises sites, accept point-to-site connections from numerous remote clients, and establish VNet-to-VNet connections to other Azure regions, all at the same time, limited only by the SKU's tunnel and throughput capacity. Site-to-Site VPN Connection. Site-to-Site VPN connections establish a secure IPsec/IKE tunnel between your on-premises network and your Azure virtual network. This is the most common VPN option for hybrid cloud scenarios where you need persistent connectivity between your corporate data center and Azure resources. The connection allows resources in both locations to communicate as if they were on the same local network. To establish a site-to-site VPN, you need a VPN device in your on-premises location with a public-facing IP address. This device must support IPsec/IKE protocols and be configured with matching encryption parameters to the Azure VPN Gateway. Azure maintains a validated list of VPN devices from vendors like Cisco, Juniper, Fortinet, and others that are known to work well with Azure VPN Gateway. The on-premises VPN device initiates or responds to the connection with the Azure VPN Gateway public IP address. The configuration process involves several key parameters. First, you define the local network gateway in Azure, which represents your on-premises network. This includes the public IP address of your on-premises VPN device and the address spaces of your on-premises network. Second, you configure the connection between the VPN gateway and the local network gateway, specifying the shared key for encryption and the connection type. The shared key must match exactly on both ends for the tunnel to establish successfully. Looking at the diagram, you can see the complete architecture of a site-to-site VPN connection. On the left side, the on-premises network contains your corporate resources and a VPN device with a public IP address. This VPN device establishes an encrypted IPsec tunnel across the Internet to the Azure VPN Gateway on the right side. The Azure VPN Gateway resides in the gateway subnet of your virtual network and provides access to all resources within the VNet, including virtual machines in application subnets. The bidirectional arrows indicate that traffic can flow in both directions through the encrypted tunnel. Site-to-site VPNs support both active-passive and active-active configurations. In active-passive mode, one tunnel is active while the other serves as a backup. In active-active mode, both tunnels can carry traffic simultaneously, providing higher throughput and better resilience. Active-active requires a VPN Gateway SKU that supports this feature in proper configuration on both the Azure side and your on-premises VPN device. Creating site-to-site VPN with Azure CLI. Creating a site-to-site VPN connection using Azure CLI involves a series of commands that provision the necessary resources and configure their relationships. The process requires creating several components in a specific order, as each resource depends on the previous ones. Understanding this workflow is essential for automation and infrastructure as code scenarios. The first command creates a local network gateway using the AZ Network Local Gateway Create command. The resource group parameter specifies which resource group will contain this gateway resource. The name parameter assigns an identifier to the local gateway, in this example on-prem gateway. The gateway IP address parameter is critical as it must be set to the public IP address of your on-premises VPN device, shown here as 203.0.113.1. The local address prefixes parameter defines the site or blocks of your on-premises network, which in this example is 192.168.0.0/16. The location parameter specifies the Azure region, here East US. This command creates the Azure representation of your on-premises network. The second command creates the VPN connection between the Azure VPN Gateway and the local network gateway using the AZ Network VPN Connection Create command. The resource group parameter again specifies the containing resource group. The name parameter labels this connection as S2S connection. The VNet Gateway 1 parameter references the name of your existing VPN gateway that you previously created in your virtual network. The local gateway 2 parameter references the local network gateway we just created, on-prem gateway. The location parameter specifies East US. The shared key parameter is the pre-shared key that must match exactly on both the Azure side and your on-premises VPN device. The third command enables BGP, Border Gateway Protocol, on the VPN connection using the AZ Network VPN connection update command. The resource group and name parameters identify which connection to modify. The Enable BGP parameter set to true activates BGP routing, which enables dynamic route exchange between Azure and your on-premises network. BGP is particularly useful in complex network topologies where you have multiple connections or need automatic failover. When BGP is enabled, routes are automatically learned and propagated without manual configuration, making the network more resilient and easier to manage. After executing these commands, you should verify the connection status. The VPN tunnel typically takes 2 to 5 minutes to establish after both sides are properly configured. You can check the connection status using the AZ Network VPN Connection Show command with the appropriate resource group and connection name. A successful connection will show a connection status of connected, and you should see traffic flowing between your on-premises network and Azure Virtual Network. Point-to-Site VPN connection. Point-to-Site VPN connections allow individual client computers to establish secure connections to your Azure Virtual Network from remote locations. Unlike Site-to-Site VPNs, which connect entire networks, Point-to-Site VPNs are designed for scenarios where individual users need access to Azure resources, such as remote workers, administrators performing maintenance, or developers accessing development environments from home or while traveling. Point-to-Site VPNs support multiple authentication methods to verify client identity before allowing connection. The most common method is certificate-based authentication, where each client must present a valid certificate issued by a trusted root certificate. Azure also supports Azure Active Directory authentication, which integrates with your organization's identity system and is particularly useful for managing user access at scale. Additionally, Radius authentication is supported, allowing integration with existing Radius servers for centralized authentication management. The VPN client software varies depending on the operating system and authentication method. For Windows and Mac OS clients, you can download a VPN client configuration package from Azure that includes all necessary settings and certificates. This package configures the native VPN client on these operating systems. For Linux clients, you can use the StrongSwan VPN client configured with the appropriate settings. Mobile devices running iOS and Android can also connect using native VPN capabilities or third-party OpenVPN-compatible clients. Looking at the diagram, you can see the point-to-site architecture. Multiple remote clients including Windows laptops, Mac OS computers, Linux workstations, and mobile devices all establish individual encrypted VPN tunnels across the Internet to the Azure VPN Gateway. Each client receives an IP address from the point-to-site address pool that you configure on the VPN Gateway. These clients can then access resources within the Azure Virtual Network as if they were locally connected. The VPN Gateway handles all the encryption, authentication, and routing for these client connections. When planning a point-to-site VPN deployment, you need to define an address pool specifically for VPN clients. This address pool must not overlap with your virtual network address space or your on-premises network address ranges. For example, if your VNet uses 10.0.0.0/16 and your on-premises uses 192.168.0.0/16, you might use 172.16.0.0/24 for the point-to-site address pool. Azure automatically assigns IP addresses from this pool to connected clients and handles routing so that traffic destined for the VNet or on-premises networks is properly forwarded through the VPN tunnel. Configuring point-to-site VPN with Azure CLI. Configuring a point-to-site VPN connection requires several steps, including setting up certificate authentication, defining the address pool for VPN clients, and configuring the VPN protocols. The Azure CLI provides commands to handle each of these configuration tasks, and understanding the parameters is crucial for successful deployment. The first command configures the point-to-site VPN settings using the AZ Network VNet Gateway Update command. The resource group parameter specifies which resource group contains your VPN gateway. The name parameter identifies your VPN gateway resource, shown here as Azure VPN Gateway. The address prefixes parameter is extremely important as it defines the IP address range that will be assigned to VPN clients when they connect. In this example, 172.16.0.0/24 provides 254 usable IP addresses for clients. This range must not overlap with your VNet address space or any connected networks to avoid routing conflicts. The VPN client protocols parameter specifies which VPN protocols clients can use to connect. In this example, both OpenVPN and IPv2 are enabled. OpenVPN is a modern, flexible protocol that works across most platforms and can traverse firewalls easily. IPv2 is the Internet Key Exchange version 2 protocol, which is particularly efficient for mobile devices, as it handles network changes well when switching between Wi-Fi and cellular connections. Supporting multiple protocols ensures compatibility with various client operating systems and use cases. The second command configures certificate authentication by uploading the root certificate to Azure, using the AZ Network VNet Gateway Root Cert Create command. The resource group and gateway name parameters identify the target VPN gateway. The name parameter assigns a friendly name to this root certificate, shown as root cert. The public cert data parameter contains the base 64 encoded public key data from your root certificate. This is the certificate that Azure will use to verify client certificates during authentication. Any client presenting a certificate signed by this root certificate will be trusted and allowed to connect, while clients with certificates from other sources will be rejected. To obtain the base 64 encoded certificate data, you first need to export your root certificate as a CER file. After these commands execute successfully, clients can download the VPN client configuration package from the Azure portal or using Azure CLI. This package contains all the necessary configuration files, including the server address, protocol settings, and routes. Clients also need to install a client certificate that chains to the root certificate you uploaded. The client certificate is used to authenticate the user to Azure during the connection process. Once configured, users can connect by selecting the VPN connection in their operating system's network settings and authenticating with their client certificate. VNet-to-VNet VPN connection. VNet-to-VNet VPN connections establish encrypted tunnels between two Azure virtual networks, enabling resources in different VNets to communicate securely. This connectivity pattern is essential for scenarios where you need to connect VNets across different Azure regions, across different subscriptions, or where you want to maintain network isolation while still allowing specific communication paths between network segments. A common use case for VNet-to-VNet connections is multi-region application deployments where you need database replication, application failover capabilities, or distributed workload processing. For example, you might have a production VNet in East US and a disaster recovery VNet in West USA. VNet-to-VNet connection allows your application in East US to replicate data to West US continuously, ensuring business continuity. Another scenario is when different business units operate separate subscriptions but need to share certain resources or services securely. VNet-to-VNet connections differ from VNet peering in several important ways. While VNet peering provides direct connectivity with higher throughput and lower latency by using Azure's backbone network, it creates a flat network space with no encryption. VNet-to-VNet VPN connections, on the other hand, encrypt all traffic using IPsec, providing an additional security layer. VPN connections have lower throughput compared to peering due to encryption overhead, but they offer the benefit of traffic isolation and compliance with regulations requiring encrypted traffic. Examining the diagram, you can see two Azure virtual networks in different regions, East US and West US. Each VNet has its own VPN gateway deployed in a gateway subnet. The VPN gateways establish an encrypted IPsec tunnel between them, shown as the bidirectional connection. Resources in VNet 1, such as web servers and databases, can communicate with resources in VNet 2, such as application servers and backup systems, through this encrypted tunnel. All traffic between the VNets is automatically encrypted and routed through the VPN gateways. When configuring VNet-to-VNet connections, the address spaces of the two VNets must not overlap. Creating VNet-to-VNet connection with Azure CLI. Creating a VNet-to-VNet connection using Azure CLI involves establishing connections from both VPN gateways to each other. Unlike site-to-site connections where you configure a local network gateway, VNet-to-VNet connections directly reference the remote VPN gateway resource. The process requires creating two connection objects, one on each side, to establish the bidirectional tunnel. The first command creates a connection from VNet 1 to VNet 2 using the AZ Network VPN connection create command. The resource group parameter specifies RGVNet 1, which is the resource group containing the first VPN gateway. The name parameter labels this connection as VNet 1 to VNet 2 for easy identification. The VNet Gateway 1 parameter references the VPN gateway in the first virtual network, named VPN Gateway 1. The VNet Gateway 2 parameter points to the VPN gateway in the second virtual network, VPN Gateway 2, which may be in a different resource group or subscription. The location parameter specifies East US, which should match the region of VNet 1. The shared key parameter provides the pre-shared key for encryption, shown here as your secure shared key 456. This shared key must be identical on both connection objects for the tunnel to establish successfully. It is used in the IPsec key exchange process to authenticate the endpoints and derive encryption keys. The shared key should be a strong, random string to ensure security. Never use simple or predictable keys in production environments. The second command creates the reciprocal connection from VNet 2 to VNet 1. The resource group parameter now specifies RGVNet 2, the resource group for the second VPN gateway. The name is VNet 2 to VNet 1, establishing the naming convention from the perspective of the second VNet. The VNet Gateway 1 parameter now references VPN Gateway 2 as this is the local gateway from VNet 2's perspective. The VNet Gateway 2 parameter references VPN Gateway 1. The location is West US, matching VNet 2's region. Critically, the shared key parameter must use the exact same value as the first connection, your secure shared key 456. Please note that the VNet Gateway 2 parameter in the first command and the VNet Gateway 1 parameter in the second command may require the full resource ID if the gateway is in a different subscription or resource group. The full resource ID format is /subscription ID /resource groups /resource group name /providers /Microsoft.network /virtual network gateways /gateway name. Azure CLI can usually resolve names within the same subscription, but cross-subscription scenarios require the complete resource ID. After creating both connections, the VPN tunnel typically establishes within 2 to 5 minutes. You can verify the connection status using the AZ Network VPN connection show command for each connection. Both connections should show a status of connected when successfully established. Traffic between the VNets will then flow through the encrypted IPsec tunnel, and you can test connectivity by pinging resources in one VNet from resources in the other VNet, assuming firewall rules and network security groups allow the traffic. VPN Gateway SKUs and performance. Choosing the appropriate VPN Gateway SKU is critical for meeting your performance, availability, and feature requirements. Azure offers multiple SKU tiers, each with different capabilities regarding throughput, tunnel count, and zone redundancy. Understanding these differences helps you select the right SKU for your workload while optimizing costs. The basic SKU is the entry-level option supporting up to 100 megabits per second aggregate throughput. It allows a maximum of 10 site-to-site or VNet-to-VNet tunnels and up to 128 point-to-site connections. However, the basic SKU has significant limitations. It does not support BGP routing, active-active configurations, or zone redundancy. It is suitable only for development, testing, or very light production workloads with minimal requirements. Additionally, the basic SKU uses the older generation of virtual machine instances and cannot be resized to other SKUs, so you must delete and recreate the gateway to upgrade. The VPN GW1 SKU represents the first tier of the modern VPN gateway family. It supports up to 650 megabits per second aggregate throughput, 30 site-to-site or VNet-to-VNet tunnels, and up to 250 point-to-site connections. This SKU includes support for BGP, active-active configurations, and custom IPsec/IKE policies. VPN GW1 is appropriate for small to medium production workloads where moderate throughput is sufficient. The SKU can be resized to higher tiers without recreating the gateway, providing flexibility as your needs grow. The VPN GW2 through VPN GW5 SKUs provide progressively higher performance levels. VPN GW2 offers 1 gigabits per second throughput. VPN GW3 provides 1.25 gigabits per second. VPN GW4 supports 5 gigabits per second, and VPN GW5 delivers up to 10 gigabits per second. The tunnel counts also increase, with VPN GW5 supporting up to 100 site-to-site or VNet-to-VNet tunnels. Higher SKUs are necessary when you need to support high-bandwidth applications, multiple simultaneous connections, or large-scale hybrid deployments. The pricing scales with the SKU tier, so you should carefully analyze your bandwidth requirements to select the most cost-effective option. Looking at the table in the slide, you can compare the key specifications across different SKUs. The SKU column lists each tier from basic through VPN GW5. The throughput column shows the maximum aggregate bandwidth each SKU can handle, ranging from 100 megabits per second for basic to 10 gigabits per second for VPN GW5. The tunnels column indicates how many simultaneous site-to-site or VNet-to-VNet connections each SKU supports, from 10 for basic up to 100 for VPN GW5. The point-to-site column shows the maximum number of concurrent client connections, starting at 128 for basic and reaching 10,000 for VPN GW5. The BGP column indicates BGP support with no for basic and yes for all VPN GW SKUs. Finally, the zone redundant column shows no for regular SKUs and available for the AZ variants. The AZ suffix variants, such as VPN GW1AZ, VPN GW2AZ, and so on, provide the same performance characteristics as their counterparts. However, they deploy the gateway instances across availability zones in regions that support zones. This provides higher availability and resilience against data center level failures. Zone redundancy is particularly important for production workloads that require maximum uptime guarantees. The AZ SKUs cost slightly more than non-AZ SKUs, but they offer significantly improved availability SLAs. VPN Gateway High Availability Options. Azure VPN Gateway provides several high availability configurations to ensure continuous connectivity even during planned maintenance or unexpected failures. Understanding these options is essential for designing resilient hybrid cloud architectures that meet your business continuity requirements and SLA commitments. The default configuration for VPN Gateway is active-passive mode. In this setup, Azure deploys 2 gateway instances behind the scenes, but only one instance actively handles traffic at any given time. The second instance serves as a standby replica. If the active instance experiences a failure or undergoes planned maintenance, Azure automatically fails over to the standby instance. During this failover, you may experience a brief interruption of 30 to 90 seconds while the connection re-establishes. The active-passive configuration is included by default in all VPN Gateway SKUs and provides basic redundancy without additional configuration. Active-active configuration provides enhanced throughput and faster failover by utilizing both gateway instances simultaneously to carry traffic. To enable active-active mode, you must explicitly configure it when creating the VPN gateway, and both gateway instances require separate public IP addresses. On the on-premises side, you must configure your VPN device to establish tunnels to both Azure gateway instances. Traffic is load balanced across both tunnels, effectively doubling your available bandwidth. If one gateway instance fails, traffic automatically shifts to the remaining instance with minimal disruption, typically less than 10 seconds. Active-active requires VPN GW1 or higher SKUs. The basic SKU does not support this feature. Zone redundant deployment distributes your VPN gateway instances across multiple availability zones within an Azure region. This configuration protects against zone-level failures, which could be caused by power outages, cooling failures, or other data center-specific issues affecting an entire zone. To deploy a zone-redundant gateway, you must use the AZ SKU variants such as VPN Gateway 1AZ or VPN Gateway 2AZ. The gateway instances are automatically distributed across zones, and Azure's infrastructure ensures that traffic is always routed to healthy instances. Zone redundancy provides the highest level of availability and is recommended for mission-critical production workloads. The diagram illustrates all three high availability configurations side by side. In the active-passive configuration on the left, you see two VPN gateway instances where only the active instance forwards traffic to the on-premises site, while the passive instance remains in standby. In the active-active configuration in the middle, both gateway instances actively handle traffic, with connections to both instances from the on-premises VPN device. In the zone redundant configuration on the right, the gateway instances are deployed across Zone 1 and Zone 2, providing resilience against zone-level failures while maintaining active traffic handling. When combining these configurations, you can achieve maximum resilience. For example, you can deploy a zone-redundant gateway in active-active mode, giving you 4 gateway instances distributed across 2 zones with all instances actively handling traffic. This configuration provides protection against both instance-level and zone-level failures while maximizing throughput. However, this also represents the highest cost option, so you should evaluate whether your workload requires this level of redundancy or if a simpler configuration would suffice. ExpressRoute with VPN failover. Azure ExpressRoute provides dedicated private connectivity between your on-premises infrastructure and Azure data centers, bypassing the public internet entirely. However, even with ExpressRoute's high reliability, a backup connection path is critical for business continuity. VPN Gateway can serve as a cost-effective failover solution that automatically activates when the ExpressRoute circuit experiences an outage. This architecture pattern, known as ExpressRoute with VPN failover, combines the performance and security benefits of ExpressRoute with the reliability of a redundant VPN connection. The ExpressRoute circuit serves as the primary path for all traffic between on-premises and Azure, providing predictable latency, higher bandwidth, and enhanced security. The VPN connection remains configured but typically carries no traffic during normal operations. When the ExpressRoute circuit fails due to fiber cuts, equipment failures, or provider issues, Azure's routing automatically switches traffic to the VPN tunnel within seconds. To implement this configuration, you need both an ExpressRoute gateway and a VPN gateway deployed in the same virtual network. Azure supports coexistence of these two gateway types, allowing you to configure routing priorities that prefer ExpressRoute over vPages N. The ExpressRoute routes are automatically assigned a higher priority through BGP attributes, ensuring that when both paths are available, traffic flows over ExpressRoute. When ExpressRoute becomes unavailable, the BGP session terminates, and routes learned via VPN take precedence. The diagram illustrates the complete architecture. Your on-premises network connects to Azure through two parallel paths. The primary path flows through the ExpressRoute circuit, which connects to the ExpressRoute gateway in Azure. The secondary path uses a VPN device on premises that establishes an IPsec tunnel through the Internet to the VPN gateway in Azure. Both gateways connect to the same virtual network, and Azure's routing infrastructure automatically manages failover between them. During normal operation, the thick arrow shows traffic flowing through ExpressRoute, while the VPN tunnel remains in standby, indicated by the dashed line. When planning this architecture, carefully consider bandwidth requirements. ExpressRoute circuits range from 50 megabits per second to 100 gigabits per second. Depending on the peering location and circuit SKU, your VPN gateway should be sized to handle at least critical production traffic during failover. While a VPN GW5 supports up to 10 gigabits per second, this is still far less than higher ExpressRoute bandwidths. So, you may need to prioritize which applications receive bandwidth during failover scenarios. Additionally, the VPN connection will experience higher latency than ExpressRoute, since traffic routes through the public internet rather than private circuits. Configuring ExpressRoute VPN coexistence. Setting up ExpressRoute with VPN failover requires careful configuration to ensure both gateways can coexist in the same virtual network and that routing behaves correctly. Azure imposes specific requirements for this coexistence scenario, particularly regarding the gateway subnet size and gateway SKUs that support coexistence. This first command creates the gateway subnet with a /27 CIDR block using the AZ network VNet subnet create. The resource group parameter specifies the resource group containing your virtual network. The VNet name parameter identifies the virtual network, shown as Hub VNet. The name parameter must be exactly gateway subnet, with this exact spelling and capitalization, as Azure requires this specific name for gateway deployments. The address prefixes parameter specifies the IP range for the gateway subnet, here using 10.0.255.0/27. The /27 prefix provides 32 IP addresses, with approximately 27 usable after Azure reserves some for internal use. This size is the minimum recommended for coexistence scenarios where you will deploy both ExpressRoute and VPN gateways in the same subnet. The second command creates the ExpressRoute gateway using the AZ network VNet gateway create command. The resource group and name parameters identify the gateway resource, here named ExpressRoute GW. The VNet parameter specifies which virtual network will host this gateway, referencing Hub VNet. The gateway type parameter must be set to ExpressRoute to create an ExpressRoute gateway rather than a VPN gateway. The SKU parameter determines the gateway's performance characteristics, with standard being the entry-level option supporting up to 1 gigabits per second. Higher SKUs include high performance for 2 gigabits per second and ultra performance for 10 gigabits per second. The location parameter specifies the Azure region, here East US. This command triggers the deployment of ExpressRoute gateway instances, which typically takes 30 to 45 minutes to complete. The third command creates the VPN gateway in the same virtual network, using the same AZ network VNet gateway create command, but with different parameters. The resource group and name parameters identify this gateway as VPN gateway. The VNet parameter again references Hub VNet, the same virtual network used for the ExpressRoute gateway, enabling coexistence. The gateway type parameter is set to VPN to create a VPN gateway. The VPN type parameter specifies route-based, which is required for coexistence scenarios and enables dynamic routing through BGP. The SKU parameter uses VPN GW1, which is the minimum SKU supporting coexistence. The basic SKU does not support coexistence with ExpressRoute. The location matches the ExpressRoute gateway at East US. This deployment also takes 30 to 45 minutes. After both gateways are deployed, you configure the ExpressRoute circuit connection and the Site-to-Site VPN connection as you normally would. The ExpressRoute connection uses the AZ network VPN connection create command with connection type set to ExpressRoute and references your provisioned ExpressRoute circuit. The VPN connection follows the standard site-to-site configuration with a local network gateway and shared key. BGP should be enabled on the VPN connection to allow proper route propagation and automatic failover. One critical consideration is routing priority. ExpressRoute routes automatically receive a higher priority through BGPAS path prepending and local preference attributes. This ensures that when both connections are active, traffic always flows through ExpressRoute. When the ExpressRoute circuit fails, the BGP session with the Microsoft Enterprise Edge routers terminates, the ExpressRoute routes are withdrawn from the routing table, and traffic automatically fails over to the VPN routes. Recovery happens in the reverse order when ExpressRoute comes back online, with a small convergence period during which both paths might carry traffic briefly. BGP configuration for VPN Gateway. Border Gateway Protocol, or BGP, is the routing protocol that powers the Internet and is essential for dynamic routing in hybrid cloud scenarios. When enabled on Azure VPN Gateway, BGP allows automatic exchange of routing information between your on-premises network and Azure, eliminating the need for manual route configuration and enabling automatic failover capabilities. BGP operates through a peering relationship between routers, where each router is identified by an autonomous system number, or ASN in Azure VPN Gateway context. Azure uses ASN 65515 by default for VPN gateways, though you can specify a custom ASN during gateway creation. Your on-premises VPN device must be configured with its own ASN, which can be a private ASN in the range 65512 to 65534 if you are not using a public ASN. The BGP peering occurs between the VPN gateway's BGP peer IP address and your on-premises router's BGP peer IP address. When BGP is enabled, routes are exchanged dynamically rather than being statically configured. Your on-premises router advertises its local network prefixes to Azure, and Azure advertises the virtual network address space and any connected networks back to your on-premises environment. If you have multiple site-to-site connections or VNet-to-VNet connections with BGP enabled, routes are shared across all these connections automatically. This creates a fully dynamic routing topology that adapts to network changes, link failures, and new connections without manual intervention. The diagram shows BGP peering between an on-premises network and Azure. On the left, the on-premises router is configured with ASN 65001 and BGP peer IP 192.168.1.1. It advertises the prefix 192.168.0.0/16 representing the on-premises network to Azure. On the right, the Azure VPN Gateway uses ASN 65515 and has BGP peer IP 10.0.255.254. It advertises the prefix 10.0.0.0/16 representing the Azure Virtual Network address space to the on-premises router. The bidirectional arrows show route advertisements flowing in both directions, with each side learning the other's networks dynamically. BGP configuration requires several specific settings. First, the VPN gateway must have BGP enabled, which you specify during gateway creation or enable later. Second, the local network gateway must have BGP settings configured, including the on-premises BGP peer IP address and ASN. Third, the VPN connection must have BGP enabled. Finally, Your on-premises VPN device must be configured to peer with Azure's BGP peer IP address using the correct ASN. The BGP peering IP addresses are typically allocated from the VPN tunnel IP address space, not from your main network ranges. Enabling BGP on VPN Gateway with Azure AZ. Enabling BGP on Azure VPN Gateway and establishing BGP peering with your on-premises network requires configuring BGP parameters on multiple resources, including the VPN gateway itself, the local network gateway, and the connection. Each configuration element plays a specific role in establishing the BGP peering session and exchanging routes. The first command creates a VPN gateway with BGP enabled using the AZ network VNet Gateway Create command. The resource group parameter specifies the containing resource group. The name parameter identifies the gateway as VPN Gateway BGP. The VNet parameter references the virtual network MyVNet. The gateway type is VPN and VPN type is route-based, both required for BGP support. The SKU parameter uses VPN GW1, which is the minimum SKU supporting BGP. The location is East US. The ASN parameter sets the autonomous system number to 65515, which is Azure's default but can be customized to any valid private ASN. The BGP peering address parameter is not specified here because Azure automatically assigns a BGP peer IP from the gateway subnet range. The enable BGP parameter set to true activates BGP functionality on this gateway. The second command creates a local network gateway with BGP configuration using the AZ network local gateway create command. The resource group and name parameters identify this resource as on-prem gateway BGP. The gateway IP address parameter specifies the public IP of the on-premises VPN device, 203.0.113.1. The local address prefixes parameter defines the on-premises network range 192.168.0.0/16. The BGP peering address parameter sets the BGP peer IP address of the on-premises router to 192.168.1.1. This is the internal IP address that Azure's VPN Gateway will use to establish a BGP peering session with your on-premises router. The ASN parameter specifies the autonomous system number of your on-premises network, here set to 65001. This ASN must match the configuration on your on-premises VPN device. The third command creates the VPN connection with BGP enabled using the AZ network VPN connection create command. The resource group and name parameters identify the connection as BGP-S2S connection. The VNet Gateway 1 parameter references the VPN gateway we created, VPN Gateway BGP. The local gateway 2 parameter references the local network gateway on-prem gateway BGP. The location is East US. The shared key provides the pre-shared key for IPsec encryption, your secure shared key 789. The enable BGP parameter set to true activates BGP on this specific connection, allowing route exchange to occur once the IPsec tunnel is established. After executing these commands, the VPN tunnel is first established using the shared key for IPsec authentication. Once the tunnel is up, the BGP peering session begins between the Azure BGP peer IP and the on-premises BGP peer IP through the encrypted tunnel. BGP uses TCP port 179 for session establishment. The routers exchange open messages containing their ASN and capabilities, and then transition to the established state. Once established, each side sends update messages containing network prefixes. Azure advertises the VNet address space and any other connected networks, while the on-premises router advertises its local networks. You can verify BGP status using the AZ network VNet Gateway List BGP peer status command, which shows the BGP peer state, routes received, and routes advertised. A successful configuration shows the peer in established state with routes being exchanged. You can also view the learned routes using the AZ Network VNet Gateway List Learned Routes command, which displays all routes the gateway has learned from BGP peers, including the next hop and path information. These verification commands are essential for troubleshooting routing issues in complex hybrid network topologies. Custom IPsec and IKE policies. Azure VPN Gateway uses default IPsec and IKE parameters that work with most standard VPN devices, but some scenarios require custom policies. You might need custom policies to meet specific security compliance requirements, to match legacy VPN equipment that only supports older encryption algorithms, or to optimize performance by selecting algorithms that your hardware can accelerate. Azure allows you to define custom IPsec/IKE policies at the connection level, overriding the default settings. IPsec, or Internet Protocol Security, provides the encryption and authentication framework for VPN tunnels. IKE, or Internet Key Exchange, is the protocol used to establish security associations and negotiate encryption parameters. IKE operates in two phases. IKE Phase 1 establishes a secure channel between the VPN peers and authenticates them using the pre-shared key. IKE Phase 2 negotiates the IPsec security associations that encrypt actual data traffic. Each phase uses separate algorithms for encryption, integrity checking, and key exchange. Custom policies allow you to specify algorithms for each phase. For IKE Phase 1, you can configure the encryption algorithm such as AES-256, AES-192, or AES-128. The integrity algorithm like SHA-256 or SHA-384. The Diffie-Hellman group for key exchange such as DH Group 14 or DH Group 24, and the SA lifetime. For IPsec Phase 2, you configure the IPsec encryption algorithm, IPsec integrity algorithm, PFS group, and SA lifetime. Stronger algorithms like AES-256 with SHA-384 provide better security but may impact throughput on devices without hardware acceleration. Weaker algorithms like AES-128 offer higher performance but reduced security. The diagram shows the IKE and IPsec negotiation process. Phase 1 begins with the IKE-SA negotiation, where both peers exchange proposals containing encryption algorithms, integrity algorithms, Diffie-Hellman groups, and authentication methods. Both sides must agree on a common set of algorithms from their configured policies. After successful negotiation, the authentication step occurs, where peers verify each other's identity using the pre-shared key. This establishes a secure IKE tunnel. Phase 2 then begins with IPsec-SA negotiation, where the actual encryption parameters for data traffic are agreed upon, including encryption and integrity algorithms for IPsec. Finally, data encryption commences with all traffic flowing through the encrypted IPsec tunnel using the negotiated parameters. Azure supports a wide range of cryptographic algorithms to ensure compatibility with various VPN devices. For encryption, options include AES-256, AES-192, AES-128, DES-3, and DES. For integrity, you can use SHA-256, SHA-384, SHA-1, and MD5. For Diffie-Hellman groups, supported options range from DH Group 1 to DH Group 24, including ECP-256 and ECP-384 for elliptic curve groups. Perfect forward secrecy groups can be set to none, PFS1, PFS2, PFS14, PFS24, ECP-256, or ECP-384. When configuring custom policies, both your Azure VPN Gateway and on-premises VPN device must support the selected algorithms. Configuring custom IPsec policy with Azure CLI. Applying custom IPsec/IKE policies to an Azure VPN connection requires using the AZ Network VPN Connection IPsec policy command with specific parameters for each cryptographic component. This granular control ensures compatibility with various on-premises VPN equipment and meets specific security compliance requirements. The command uses a Z-Network VPN Connection IPsec policy add to attach a custom policy to an existing VPN connection. The resource group parameter specifies which resource group contains the connection. The connection name parameter identifies the specific VPN connection to modify, here shown as S2S connection. This allows you to apply different policies to different connections if you have multiple site-to-site VPNs. The iKey encryption parameter specifies the encryption algorithm for iKey Phase 1, set here to AES-256. This means the iKey negotiation traffic itself will be encrypted using AES with a 256-bit key. AES-256 provides strong security and is widely supported by modern VPN devices. The iKey integrity parameter defines the integrity checking algorithm for iKey Phase 1, here using SHA-256. This algorithm ensures that iKey messages have not been tampered with during transmission by computing a cryptographic hash of the message. SHA-256 provides strong protection against message modification attacks. The DH group parameter specifies the Diffie-Hellman group used for key exchange in IKE Phase 1, set to DH group 14. Diffie-Hellman is the algorithm that allows two parties to establish a shared secret over an insecure channel. DH Group 14 uses a 2048-bit key, which is considered secure against current attacks and is required by many security compliance frameworks. Higher groups like DH Group 24 use 2048-bit elliptic curve keys for improved performance with equivalent security. The IPsec encryption parameter defines the encryption algorithm for IPsec Phase 2, which encrypts the actual data traffic. Here, it is set to AES-256. All user data flowing through the VPN tunnel will be encrypted using AES with a 256-bit key. The IPsec integrity parameter specifies the integrity algorithm for IPsec, using SHA-256 to ensure data has not been modified. The PFS group parameter configures perfect forward secrecy using PFS-14. PFS ensures that if one session key is compromised, past and future session keys remain secure by generating new Diffie-Hellman keys for each IPsec security association. The SA lifetime parameter sets the security association lifetime to 3,600 seconds, which is 1 hour. After this time expires, the IPsec security association is renegotiated, and new encryption keys are generated. After applying this custom policy, you must configure your on-premises VPN device with identical parameters. The device must support AES-256, SHA-256, DH Group 14, and PFS-14 for the connection to establish successfully. If the algorithms do not match, the IKE negotiation will fail, and the VPN tunnel will not establish. Most modern VPN devices support these algorithms, but you should verify your device's capabilities before configuring custom policies. You can use Azure CLI commands or the portal to verify that the policy has been applied correctly to your connection. VPN Gateway Monitoring and Diagnostics. Monitoring your VPN gateway is essential for maintaining reliable connectivity and quickly identifying issues before they impact users. Azure provides comprehensive monitoring capabilities through Azure Monitor, including metrics, diagnostic logs, and connection health indicators that give you visibility into gateway performance and connectivity status. Azure Monitor metrics provide real-time and historical data about VPN gateway performance. Key metrics include tunnel bandwidth, which shows the aggregate bandwidth being used across all tunnels and helps identify capacity constraints. Tunnel ingress bytes and tunnel egress bytes measure the amount of data flowing through the gateway in each direction, useful for billing analysis and capacity planning. Tunnel packet drop count indicates packets being dropped, which can signal network congestion or configuration issues. BGP peer status shows the state of BGP peering sessions, critical for dynamic routing scenarios. Diagnostic logs capture detailed information about gateway events and operations. The Gateway Diagnostic Log records connection establishment and termination events, IKE negotiation details, and configuration changes. The Tunnel Diagnostic Log tracks all traffic flowing through IPsec tunnels, including source and destination IPs, protocol types, and port numbers. The Route Diagnostic Log shows route changes learned through BGP or configured statically. The IKE Diagnostic Log provides detailed information about IKE Phase 1 and Phase 2 negotiations, essential for troubleshooting connection failures. The diagram shows the monitoring architecture. Azure VPN Gateway generates multiple types of data flowing to different Azure services. Metrics stream continuously to Azure Monitor Metrics, where you can create charts, set up alerts, and analyze trends. Diagnostic logs flow to multiple destinations simultaneously, including Log Analytics Workspace for advanced querying and correlation, Azure Storage Account for long-term archival, and Event Hub for streaming to external monitoring systems or SIEM solutions. Azure Monitor alerts can be configured on any metric or log query to send notifications when thresholds are exceeded or specific events occur. Connection Monitor is another powerful tool that actively tests connectivity through your VPN gateway to specific endpoints. You define source and destination pairs, and Azure regularly attempts to connect through the VPN tunnel, measuring latency, packet loss, and reachability. This proactive monitoring detects connectivity issues even before users report them. Connection Monitor can test connectivity from Azure virtual machines through the VPN to on-premises resources, verifying end-to-end reachability. Network Watcher provides additional diagnostic capabilities including VPN troubleshooting, which runs automated diagnostics on your VPN gateway and connections to identify common configuration issues, connectivity problems, or performance bottlenecks. The tool checks IPsec parameters, BGP configuration, routing tables, and security group rules, providing specific recommendations for remediation. Packet Capture allows you to capture network traffic flowing through the gateway for detailed protocol analysis, useful when troubleshooting complex connectivity issues that are not obvious from metrics and logs alone. Configuring VPN Gateway Diagnostics with Azure CLI. Enabling diagnostic settings on your VPN gateway allows you to collect detailed logs and metrics that are essential for troubleshooting, compliance, and performance optimization. The Azure CLI provides commands to configure where these diagnostics are sent and which log categories and metrics to collect. The first command creates a log analytics workspace using the AZ Monitor Log Analytics Workspace create command. The resource group parameter specifies the resource group that will contain the workspace. The workspace name parameter assigns the identifier VPN gateway logs to this workspace. Log analytics workspaces provide a centralized repository for log data from multiple Azure resources and offer a powerful query language called KQL, or Custo Query Language, for analyzing logs. The location parameter specifies East US. The workspace must be created before you can configure the VPN gateway to send logs to it. The second command retrieves the resource ID of the VPN gateway using the AZ Network VNet Gateway Show command. The resource group and name parameters identify the VPN gateway Azure VPN Gateway. The query parameter uses JMES path syntax to extract just the ID field from the command output, which returns the full resource ID string. The output parameter set to TSV formats the output as tab-separated values, producing clean output suitable for storing in a variable. This resource ID is needed when configuring diagnostic settings because it uniquely identifies which resource the diagnostics apply to. The third command creates diagnostic settings for the VPN gateway, using the AZ Monitor Diagnostic Settings Create command. The name parameter labels this diagnostic configuration as VPN Gateway Diagnostics. The resource parameter uses the variable containing the VPN Gateway resource ID that we retrieved in the previous command. This tells Azure which resource these diagnostic settings apply to. The workspace parameter specifies the log analytics workspace ID where logs and metrics will be sent. You can obtain this ID using the AZ Monitor Log Analytics Workspace Show command, or from the Azure portal. The logs parameter defines which log categories to collect, using a JSON array format. Each object in the array specifies a category and whether it is enabled. The categories shown include Gateway Diagnostic Log, which captures connection events and gateway health information. Tunnel Diagnostic Log records tunnel traffic details. Route Diagnostic Log tracks routing changes. And IKE Diagnostic Log logs IKE negotiation details. The metrics parameter specifies which metrics to collect, and is defined using a JSON array. The category All Metrics includes all available metrics, such as bandwidth utilization, packet counts, BGP peer status, and connection counts. The enabled field, set to true, activates metric collection. Metrics are typically sent to Azure Monitor Metrics automatically. VPN Gateway Security Best Practices. Securing your VPN gateway is critical to protecting your hybrid cloud environment from unauthorized access, data breaches, and cyber attacks. Implementing security best practices ensures that your VPN infrastructure meets compliance requirements and maintains the confidentiality and integrity of data flowing between on-premises and Azure. VPN Gateway Cost Optimization. Azure VPN gateway costs can become significant in large deployments, making cost optimization an important consideration for cloud architects. Understanding the pricing model and implementing best practices for cost management helps you maintain secure connectivity while controlling expenses. VPN gateway costs consist of several components that bill independently. The primary cost is the gateway compute charge, which is a fixed hourly rate based on the SKU you select. Basic SKU costs the least, but has limited features and performance. VPN GW1 through VPN GW5 SKUs have progressively higher hourly rates corresponding to their increased throughput and tunnel capacity. Zone redundant variants with the AZ suffix cost approximately 15 to 20% more than non-AZ SKUs, but provide higher availability. The gateway compute charge continues 24/7 as long as the gateway exists, even if no traffic flows through it. This means you pay for availability, not usage. Data transfer costs apply to all traffic exiting Azure through the VPN gateway to on-premises or VNet-to-VNet destinations. Inbound data transfer to Azure is free, but outbound data transfer from Azure incurs charges that vary by region and volume tier. The first 5 GB per month is free. Then pricing follows a tiered model where costs decrease as monthly volume increases. For example, the first 10 terabytes might cost more per gigabyte than data transfer beyond 50 terabytes. These costs can accumulate quickly for data-intensive workloads, so monitoring and optimizing data transfer is important. The table in the slide compares cost components across different scenarios. The gateway compute column shows monthly costs for running the gateway infrastructure. Right-sizing your VPN gateway SKU is the most effective cost optimization strategy. Many organizations over-provision gateways by selecting high SKUs without measuring actual throughput requirements. Monitor bandwidth utilization using Azure Monitor Metrics over several weeks to understand peak and average usage. If your gateway consistently operates below 50% of its SKU capacity, consider downgrading to a lower SKU. However, ensure you account for growth and traffic spikes. Consolidating connections reduces gateway costs in multi-site scenarios. Instead of deploying separate VPN gateways for different business units or projects, use a hub-and-spoke topology where a single gateway in the hub VNet serves multiple spoke VNets. For non-production environments, consider using the basic SKU, or even stopping and deallocating gateways when they are not needed. Development and testing environments often do not require 24/7 connectivity or high throughput. You can automate gateway start and stop using Azure Automation Runbooks. These can turn on gateways during business hours and shut them down overnight or on weekends. Thank you for your attendance. Please consider subscribing to the channel and liking this video.